So in this video, we're going to dig into Schrodinger's equation. So now we're looking at a new set of quantum rules, one that deals with function, a wave function, rather than an infinite dimensional column vector. And so we define this wave function to be the probability amplitude that if you were in the state psi to measure the x position of it. And normally that would be a value at every location in space, but that just gives me a function. So that's how we define the wave function. It's the probability amplitude. And then our second rule is if we multiply it by its complex conjugate, that gives me the probability of finding the particle. And we have to make sure it's normalized. So if we look at it at every location, integrated over every location, it has to be one, it has to be someplace. And so that's what our normalization is. So usually when we get our psi, we have to make sure that it's normalized this way. Okay, the third rule was the same. We have a operator for every observable, except our operators before were all matrices. Now they're going to be like functions. We still have our eigenvalue, eigenvector equation, but now we operate on functions. The average value, we still sandwich it in and do a dot product, add them all up right here, and the uncertainty in that average value. And then the last one was Schrodinger's equation, where we actually put in the operator for the Hamiltonian, which this just came out to be the kinetic energy, and this is the potential, and this is the total energy. So on this one, I want to look at this a little bit more. So let me start with that function, minus h bar squared over 2m partial squared psi of x and t with respect to x squared plus u of x psi of x and t equals I h bar partial psi of x and t with respect to t. Now, they don't teach you how to solve these here at this school, but it's a very simple way to solve partial differential equations, at least for this one right here. What we're going to do is we're going to say, let's let big psi of x and t, why don't we separate out the x part from the time part? So I'm going to call it psi of x, where this psi doesn't have the lines on the top and bottom, so that's the lowercase psi, times some function of time. We can do that. These are kind of independent of each other. So the x doesn't depend, so these are independent, so we can write it like this. So now, let me take this and put it up into here. If we do that, we start out with minus h bar squared over 2m. But now, if I take the derivative of this, I can pull the time part out in front because you're not taking the derivative with respect to you're not taking the derivative with respect to time, so I'll pull out the time part. And now the only thing that's left in the second derivative is that term, and that I can turn the partials into total derivatives. So that just becomes the second derivative of psi of x with respect to t. Why? Because it's only a function of x, and the partial and the total are exactly the same, dx squared. Okay, and then plus u of x, and then for that we're going to plug in the product of the two, psi of x, t of t, equals I h bar. I can pull this x part out in front of here because you're just taking the derivative with respect to time, so I'll pull out the psi of x part. And then you're only left in the partial derivative, you're only left with the t. It's only a function of t, so the partial and the total are exactly the same. So I can turn this into dt, dt. Okay, so now I've turned a partial differential equation into a total differential equation. The next step, what I'm going to do is I'm going to divide every term by psi of x, t of x. Psi of x, t of t. Divide every term by that. Okay, so this term right here, the t will be gone, and I'll have an extra psi in the bottom. So this first term will be minus h bar squared over 2m, 1 over psi of x. And then d squared psi of x, dx squared. Plus, and then since we're dividing by that, these two both cancel out, and we just get plus u of x. And then on the right-hand side, we get I h bar. Since I'm dividing by this term, the si's drop out, and we get 1 over t. dt dt. Okay, that should still be okay. Okay, now you'll notice that everything in this equation is just, there's no time in this part, it's all x's. This is just some function of x. You'll notice that this has no x's in it, it's just a function of time. And these are equal to each other. And this equation has got to be true for all x's and all times. So if I kept x fixed and just changed the time, this equation should still hold. Or if I just kept time fixed and changed the x, this equation should still hold right here. The only time this will ever happen, f of x equals g of it, if t on the other side, is if these are both equal to a constant. So this equals that has to equal some constant. It has to, otherwise you can't vary this and vary x and keep time the same and keep these this equal unless this is equal to a constant and that's equal to a constant. So now I have two equations. I have this is equal to my constant and I have this equals to my constant. So now I have I h bar 1 over p sub t dt sub t dt equal to some constant. And we also have this equal to some constant, minus h bar squared over 2m, 1 over psi of x, d squared, d second psi of x, dx squared, plus u of x equal to that same c. So what I did was I turned one partial differential equation into two, and this is of two variables, into two equations, and each one is just a total differential equation. So now I've simplified quite a bit. Now I just have to solve these two right here. Well, it looks like the top one is the one we'll tackle first right here. So if we tackle this one right here, once I get t of t and psi of x, I can multiply them together and get what I'm looking for. Okay, well, what I think I'll do over here is I'll take the little t and put it on the other side, the dt. So over here we have I h bar d big T all over big T equals, and I'm just going to take the dt on the outside, c dt. Okay, well, we can get rid of we can integrate both sides. So if we just integrate both sides to get rid of the d. Then this becomes I h bar dt over t. That's the natural log of t equals c t. Oh, but you got a constant in there too. Let me call the constant c prime plus c prime. That's my constant. Well, let's divide both sides by IH bar. So we got the natural log of T sub T equals C over IH bar T plus C prime over IH bar. But C prime over IH bar is just another constant. That'll be just absorbed into my C prime. I could call it C double prime, but it's just a constant. Okay, and now I want to get rid of my natural log, so we'll put both to the e power. And so this is T sub T equals e to the... Now if I take that I and bring him up to the top, he becomes minus I. Remember, 1 over I is minus I C over H bar T times e to the c prime. Well, e to the c prime is just another constant. So I can just turn that into another constant, and I can bring it out in front. So we can say t of t is just some constant c prime, e to the minus I c over h bar t. Now, I don't even need to put the constant in there, because I'm probably going to get a constant in the other equation. And so when I put them together, I can absorb the constant in the other term right there. Not only that, once I normalize it, I might have to multiply it by a constant anyway to make sure that it equals 1. So I really don't need the c prime in there. Okay, so that is our t sub t. Now we'd like to get that c in there. Now if we come back to this second equation right here, I'm going to multiply everything by psi, this psi. So this becomes minus h bar squared over 2m and then this is gone because I'm multiplying it, and I got the second derivative of psi of x with respect to x squared plus u of x psi of x equals c. And then I multiplied everything by psi, so I'm going to have a psi over here, psi of x. Okay, now if you look at this right here, remember we said the energy operator, our h right here, which was our energy operator, was minus h bar squared over 2m. It was a second derivative, but since we have no time here, I can just write, I can say total derivative, I guess, with respect to x squared plus u of x. Well, you'll notice that all of this right here is just my h acting on psi. So this is just, the whole left side was just h acting on psi. And what do we have over here? We have, on the right-hand side, we have c acting on psi. Oh, well that looks like, that just looks like this equation right here, our eigenfunction, eigenvalue, and whatever's in front is whatever you read. Well, if I apply the energy operator on psi, I should get the energy values that I read times psi. So C is the energies right here. C is equal to the energy. So I can come down to here, and we know what that C is. That's e to the minus IE all over h bar t. Now I should say this isn't going to change for any specific, whatever, it has nothing to do with the forces on it. because that's in a different equation right here. And since this is always true, this is always going to be true right here. So it's not like we're going to get a different t sub t later. That's it for quantum mechanics right here. And so what is this doing? This thing is just, remember, on our complex plane right here, this is our imaginary part, and this is the real part. Isn't that thing just going around like this? That point, t sub t, is just a point going around, a unit circle right here. That's kind of strange. Time has a strange relationship in quantum mechanics. It's just a point going around in a complex plane. So it's going from 1 up to I to -1 to -I. That's all it's doing right here. Not only that, we can see what the magnitude of that value is. Remember, the magnitude, you multiply it by its complex conjugate. Well, if you multiply that by its complex conjugate, you just get 1, because you get e to the minus times e to the plus. It just gives you e to the 0, which gives you 1. Okay, so this, well, let me write it back like this one up here, or this. These are both the same equation. I'm going to rewrite it. So now we have minus h bar squared over 2m d squared psi of x dx squared plus u of x psi of x, and that equals my c, which is my energy, psi of x. So that and that are both the same equation right there. Okay, this is called Schrodinger's time-independent equation. This one over here was Schrodinger's time-dependent equation, but we pulled the time out, so this is Schrodinger's time-independent equation. Independent equation in one dimension. Okay, this is what we're going to be using. Remember, the whole purpose of these eigenvalue, eigenfunction equations is I give you an h, and what do you get out? You get out the eigenvalues. Actually, let me replace that with just e, since we know c is e. So what are we going to get out of this when we plug into this equation? We're going to get a bunch of e's. We're going to get an e1. We're going to get an e2, dot, 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 right there. Maybe an infinite number of them, because since this is an infinite dimensional space right here. And for each eigenvalue, we get an eigenfunction, which is psi1. We get a psi2, psi3, doing dot, 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 all the way down. And these guys will be our basis states. I can't call them vectors anymore. They're all going to be orthonormal. That is, if I integrate psi I star psi j dx, I'm going to get 0 when they're different and 1 when they're not, when they're the same. So that's going to be that, again, that Kronecker delta right there. They're all orthonormal. Now, before I made the measurement, I didn't know which one I was at, and so before we were at psi of x, it was a combination of all of them. It was alpha 1 psi 1 plus alpha 2 psi 2 plus dot, 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 dot. Where this times this complex conjugate is the probability of measuring psi 1, this squared is the probability of measuring psi 2, and so on. And if I measured, say, E1, this state would collapse to just psi 1. If I measured E2, this big thing would collapse to just state psi 2 right there. Now, if I wanted to know what this is not big psi, this is little psi. If I wanted to now put this part into it and say, what is big psi right here? Big psi of x and t would just be alpha 1 psi 1, which is a function of x, And I would just put in this, e to the minus I e1 all over h bar t. If I haven't made any measurement, then I've got all of these, plus alpha 2 psi 2 of x e to the minus I e2 over h bar t plus dot, 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 dot. Okay. But if I came over here and measured just E1, I know everything would just collapse down to this right here. If I measured E2, everything would collapse to just that. So now we can, and again, once we have the size, once we even have this or this, we can measure what? The average value of these things, how well you can measure, what's their standard deviation. We can measure for any observable. Okay. So what we're going to be doing on this is we're going to be throwing in a potential energy into here. That's what we're going to be throwing in. You put in the u of x, which is like the forces on it. And what comes out? These guys come out right here. We get these out. So out comes the psi x's, psi x, and the energies. I guess I should say i's, since we got a whole bunch of them right there. Okay, you get a... So, now, now we're down to just solving this right here. How do we solve this equation right here? Well, so let me write this equation over here again. This is what we're going to be solving. Minus h bar squared over 2m d squared psi dx squared plus u of x psi of x equals e psi of x. Now, there are certain, when we solve for psi right here, remember this is a function. Psi is a function is what we're trying to find. Now, so if you were to plot out psi as a function of x, first of all, the psi can't be like this. It can't be discontinuous. It has to be a continuous function. Why? Because if it was discontinuous right here, what is d psi dx? Then that's like infinity. And then when you took the second derivative, then it certainly isn't going to be a finite number right here. So one of the properties of this is psi must be continuous. And the derivative of it has to be continuous. So psi of x and d psi dx should be continuous. Be continuous. Okay, so there's one thing we also psi has to be single valued too, right? You can't have two values for psi because when you make a measurement, you're not going to get two values, you're only going to get one. We can also say that psi at plus or minus infinity has to go to 0. Has to. Why? Because we said the area under the curve, this right here, this is finite. It's 1. So if you were to plot out psi, so, let's just say your psi is something like this, keeps going up. The area under that curve is not going to be 1. The only way that the area under that curve is going to be a finite number is if this thing has to go, you have to go down to 0 out at the ends. Otherwise, the area under that curve, when you square it, won't be 1. Okay, so we kind of already know what a lot of it's going to look like. The rest of it in between kind of depends on what the potential is right there. Well, let's look at it for just a arbitrary potential. Suppose our potential energy looks like actually I don't want to draw it so big right here. Need some space. We'll just say it's like that. There's my potential. U. I don't know where to put the origin, but I don't know if it matters right here. But let's just say here you got U of x. I could put the origin here, I guess. So there's my U as a function of x. Now I say, what does the wave function psi going to look like? Just for that picture right there. I'm going to draw it underneath of it with the same, on the same x scales, but this is now going to be my psi of x. Okay. And so, what do we know right here? First of all, it kind of depends on what the energy of the system is right here. So let me let's assume that the energy on here is, let's say I'll pick an arbitrary spot. How about right there? There's what the energy is. Energy of the particle. There's E. Now you'll notice that if this were a block on a bowl shape, just like we had with that potential energy, if I put the block right there and just let him go right there, because if he has right there, that was his total energy when he's right there is E. We let him go, what would he do? He'd drop a little bit, pick up some speed, and then he'd come over to here, and he'd probably just kind of oscillate back and forth right here. He couldn't make it up out of that because he doesn't have enough energy. He's only got this much energy right here. Okay, and I'm even going to, right where these two cross, I'm going to put a dash line down here. Another dash line down here. Okay. So what does the psi look like? We already said out at infinity, it's got to go towards 0. So that means that over here, it's either going to go down like this, or it could come from down up below. It's got to be one of those. It can't be anything else when you come way out to infinity. Same with over here. It's either got to go like this, or it's got to go like that. Independent of what this picture looks like right here, as long as it's bound, you know. If you're free, then everything's off right here. We're always going to be bound right here. Okay, so now we've got that. Okay, now we just need to figure out what happens in between these two right here. Now we know it can't be 0 all the way across like this, because the area has to be, when you square this, has to be 1. And you would have no area if it was just along the x-axis. Well, if we come back up to this thing, and we solve for the second derivative of psi with respect to x squared. Now, instead of putting the h bar squared over 2m, I'm going to throw everything on the other side and just say it's proportional. This is the proportionality constant. This is proportional to, I don't want to lose the minus though. If I throw the u on that side, it'd be e minus u, but if I threw the minus over there, it'd be u minus e. So we would have u of x minus e times your psi of x. I mean, that proportionality, I could put that in there. It's equal to 2m over h bar squared right here. Maybe I'll just put it back in, forget the proportionality. This is just 2m over h bar squared. Okay, remember from math, the second derivative of a function tells you its concavity. And the concavity, if it's positive, then it kind of goes like this right here. And if it's negative, it kind of goes like this right here. Well, you'll notice over here, in this region, from here over, the U is bigger than the E. U is way up there, E is down here. If U is bigger than E, then this is a positive number right here. If U is bigger than E, I just wanted to make sure I got that right there, just to make sure. It's proportional to U minus, yeah. If U is bigger than E, then this is a positive number. And if psi is up here, then if it's up here, it's positive. It's down here, it's negative. If psi is up there, then it's also a positive. So this is all positive in this region. That means you're concave up. So in this region, you're concave up right there. Down below, if this is positive, but this is negative because you're down here, then this whole thing is negative and you're concave down. So it's like this if you're down there. Likewise, it's going to be the same over here because U is bigger than E. So if you're in this region, you're concave up, and if you're in this region, you're concave down. Now, in the middle, between those two, E is bigger than U right here. So E is bigger than, this is negative right here. So if psi is positive and you're up here, that means this whole thing is negative and you're concave down. So anywhere in this region, you're going to be concave down. Anywhere in this region, you're going to be concave up. Okay, well, then that probably already tells me what my solution is. What's one possible solution? One possible solution would be, well, let me see. You see this little part right here? This is a concave up. And so we could just come up to there. That's just this little part of my concavity right there. I want this to go down to 0 because if there's ever a little hole there, it's going to start heading back up again. I don't want that to happen. Same with over here. We could have just done that right there. There's one possible solution. And then over here, well, heck, I can just need to make it concave down. Well, there is a solution. There is a good solution for that potential right there. Now, that's not the only one right there. Let's see. I could have just flipped it. We could have done this right there. It would have been exactly the same, but that would be the same answer. It wouldn't be a different state. It would be exactly the same state right here. So I wouldn't help just by flipping it. It's just like multiplying. All it would be is like multiplying everything by a -1. It doesn't change the equation at all. Okay, but I could see another one in here. Right, we could have said, well, this thing is coming in like this. Except here, I could say, well, it's going up like this. That's still concave. And then down here, oh, now it's got a concave back up again. Oh, and then it comes over to here. Well, that's a possible solution too. Not only that, this one has a smaller wavelength. You can see this is a pretty big wavelength right here. And we know there's a relationship between energy and wavelength. Energy is HF, which is HC over the wavelength. The bigger the wavelength, the smaller the energy. So this would be the smallest energy that you could possibly get. I can't wiggle any less than that. So we could call this one, say, psi1. This will end up being probably my psi1 corresponding to my lowest energy. This would be my psi1. Corresponding to my lowest energy, E1. And then this next one right here, shorter wavelength, this would be my psi2, probably corresponding to my E2. And these two would be orthonormal to each other as long as they'd be orthogonal. That is, if I integrated the green one times the red one, I would get 0. Well, we could go to the next one. The next one is, maybe I could come up to here, and then I could go like that. Come back down to here. So this one would be the third one, psi 3. And this, you notice, I can keep adding more and more wiggles in here. There's no limit to it. So I could have E1, E2, E3, as long as, but every time I add more, this energy is going up because the red one had the lowest energy, and then the next and next. And if this thing ever went like that, if I could ever get above this line right here, then I'm free. So we won't do that for now. We'll just keep it going up. Keep going up. And if we keep going up on both sides, then there'd be an infinite number of solutions here. So these are what we want to find. All of these infinite number of psi's and infinite number of energies, they all come out of this equation. All these psi's and all these e's. So on the next one, we will actually do it for a specific case, for a specific U, and work on it for multiple lectures so we can really beat it to death right here. But this is really what we're doing, and we know what the function is going to look like. Have to be continuous, go to 0. Out at infinity, it must be the slopes and the values have to be continuous. And we saw from concavity, anytime your U is below the energy, you're just going to wiggle back and forth. And anytime your U is bigger than E, you're probably just going to exponentially die out on both sides right here. Okay, so hopefully this gives us a little feel for how to solve this equation. But we'll get some practice on the next one.